I will show how to calculate natural frequency in shapes using robot structure analysis software. And I'll also do it by hand calculations. So the example is on page 22 in the notes. And the span of the frame is 4 meters. And the height of each story is 3 meters. And it's a 3-story frame on fixed supports. 4, 3, 3, 3. All beams and columns have rectangular 200 by 30 millimeter sections. By 30 millimeter. And density of steel is 7880 kilogram per meter cubed. These are in meters. And Young's modulus is 200. Kilonewton per meter squared. And each beam carries additional mass of 2000 kilograms. I will start analyzing this in a robot. I'll start with a new 2D frame model, and I will place first on the axis in the horizontal direction, just one repetition, and the distance is 4 meters. And in the Z direction, I will change this to ABC, and it's 3 repetitions for 3 stories, and the distance is 3 meters. Close. So this helps to create the frame. Now for the columns, the section is basically in the longer dimension of the section is perpendicular to the plane, so the frame basically oscillates in this plane, XY plane. So if this is XY plane, that means that the 30 dimension of 30 is in the X direction, and direction of 200 is in the direction normal, so Z. So basically the frame is thin and long in terms of its section. And that is for the column. For the beams, beams have to carry additional load of 2000 kilograms. So I will calculate how much that will add to the beam cross section. So this additional area of the beam cross section I can find if I divide the mass that needs to be added of 2000 by the density. So this is giving me the mass in meter cubes, and if I divide this by the length of the beam as well. This gives me the required area that needs to be added to the beam section. And I will calculate 2000 divided by 7880 divided by 4 equals 0,0635 meters squared. And if I know that the dimension, horizontal dimension for the beam is 30, that means that the vertical dimension D is equal to this 0.0635 divided by 0.2, and this is 0.317 meters. So this is my beam cross section. Not like that. So originally my beam was this one, 30 millimeter by 200, but now this has been added 317 millimeter. And so now the new depth for the beam is 347 millimeter. There are two reasons for making this adjustment. One is to incorporate the mass which is added and spread it along the beam. Another reason is to give the beam more rigidity by adding its depth. It becomes more close to the assumptions of the rigid frame, which is that beams are rigid. So now that the beam section has been increased, it is more rigid. Now I'm going to go back to Robot and create these cross sections in sections materials. So both are made of steel, and I will add new section, parametric, and it will be a rectangular section. So I will call this first one column, or call, doesn't matter. And the column width is, this is in millimeters, so it's 200, and the height is 30, and it's solid. And add. Next one, I'll do beam. Same width, but the depth is 347. And close. So now that I have added the sections, I can create members. Because I have the grid lines, I don't need to put the nodes. I already know where the nodes are. And I will place, let's place first the beams, the columns. So column, if I click on drag, I can do it a bit more easily. So these are my columns, press escape, and now beam. I don't need the drag now. So I'll start, it doesn't matter really. I'll start from the top And I created three beams, and I can now show their cross sections. So the column is clearly thinner. This shows here that the column is thin in the plane of the frame, which also counts for the frame in the experiment. And the beam is quite rigid, quite a bit stiffer than the column for deformation in the plane. I can now turn off these sections, and I can also go back to the 2D view, and I will need to add supports. Supports are fixed, and that's it. That's it. I can also go into loads and create a dead load. This is the load which contains all the self-weight. So dead load 1. And now I can do the frequency analysis by going to analysis type, new, model. Number of modes, I will put 3 because I have 3 stories, so 3 degrees of freedom. And I will leave everything else as it is. And I will run calculations and close. Now I can go to results. Go to results and show deformation, nodal displacement, apply, and also parameters, apply. No, sorry, labels, apply. So this is showing, it's quite a small displacement in due to the dead load. It's only 0.1 millimeter, but we don't care about this. It just shows that the dead load is actually applied. What we need is to go to the model load case and change to mode 1, and then in the deformation, it's quite big, quite a bit bigger than the vertical one was, so that's why it's showing so big. So it's telling us the frequency is 0.41, and the first mode is this one. If higher accuracy is needed, tools, units, and formats. And this one is other displacement, and I will add one more. Okay, so that's basically to make it a bit more accurate. So I can now take a screenshot. This is the first mode, frequency is 0.41. Okay, so that is the first mode oscillations. Now, in the same way, I'll display mode 2. This is mode 2. And the frequency is 1.16. So frequency 2, 1.16 Hertz. And then last one, mode 3. Mode 3 with 3 crossings. This is a bit simpler than using snipping tool. And this is 166. And so F3 is 166 Hertz. Okay, so now we have these results from robot. We can check them by hand calculations. First of all, we can form the mass matrix. Mass 1 is equal 2000 kilograms plus the mass of the original beam, which is 0.2 times 0.03 times 4 times 7880. So this is volume of the beam times density, and plus mass of the column, which is 0.2 times 0.03 times the length is 3 meters and 3 meters. So for the first mass, this is basically our mass 1. So beam plus 3 meters of column. And times 7880. Mass 2 is the same. And mass 3 will have the same 2000, the same beam, but instead of 3 plus 3, it will just have 3. It's a tiny bit of difference. And I should calculate. So this is 0.2 times 0.03 times 7880 and times 4 plus 6, 10 plus 2000 equals 2473. And take away 0.2 times 0.03 times 7880 times 3, 2330. And 3 is equal to 2330 kilograms. Now the stiffness, K1 equals K2 equals K3 equals 2Kc, and each stiffness is 12 times AI over L cubed. So this is 12, 2 times 12 times 2 times 10 to the 11 times I, which is 0.2 times 0.03 cube over 12, and times L cubed, which is 3 cubed. So 12 and 12 will cancel, so it's 4 times 0.2 times 0.03 cubed times 10 to the 11 divided by 3 cubed, and I get 80,000. Let's check again. 0.2 times 0.03 cubed times 4 to the power 11 divided by 3 cubed equals 80,000. Okay. Now I can write the mass matrix. 2473, 2473, 2330, 0, 0, 0, 0, 0, 0, and the K matrix, K1 plus K2, which is 16 minus 8 minus 8, K2 plus K3, 16 minus 8 minus 8 and 8 times 10 to the 4. So this is K1 plus K2 minus K2, 0, minus K2, K2 plus K3 minus K3, 0, minus K3, K3. And now I can make the A matrix, which is M inverse times K. And for this now I can use MathCAD. I can just put in the two matrices. So M matrix, and here I will have 3 by 3. Yeah. So this was the first one was 2473. So this is free software. Two three three zero and K equals again 3 by 3. The first one is 16 minus 8, 0, minus 8, 16, 0, not 0, but minus 8, 0, minus 8, 8. Everything times 10 to the power of 4. And now A matrix is equal M matrix inverse times K. Which is this one. And then eigenvalues L, so G, control G for Greek, is equal eigenvalues of A, which is equal. So we have, they are not ordered correctly, but the first one is 6.614. So the frequencies are equal square root of lambda of eigenvalue divided by 2 pi equals, so these are our values for natural frequency from robot. So the first natural frequency 0409, I can actually copy this from Mascad first. Just made our life a bit easier. So now that we have these, the A matrix, and we have the natural frequency and the frequencies and the eigenvalues, we can actually do the calculation now of the eigenvectors. I could do it in Mascad as well, but anyway, so these are matching what we got before relatively closely, which was 041, 116, 166. 041, yeah, close, 116, relatively close, 166. So small percentages. And now what will be our equation? The first equation is 64.7 minus eigenvalue 1, which is 6.61, times x1 minus 32.3 x2 equals 0. And the second equation, minus 32.3 x1 plus 64.7 minus 661, which is lambda 1, x2 minus 32.3 x3 equals 0. So how are we solving this? We're making x1. We can write the third equation, but we don't have to because we have enough. X1 is equal to 1. Then x2 is equal 64. Sorry, x2 is equal 64.7 minus 661, which is 58.1 divided by 32.3. 1.8. And then with these values, x3 is equal to so it's minus 32.3 plus in bracket 64.7 minus 6.61 times 1.8 divided by 32.3, and that is 2.24. So that means this was our first mode. That means our first mode shape is 1, 1.8, and 2.24. What do we have in robot? In robot, x1 for the first mode, 6.8, 12.1, 15. Now, how can we find if this is the same? Well, simply we divide it by the first number. So 6.8 divided by 6.8 is obviously 1. 12.1 divided by 6.8, 1.78, and 15 divided by 6.8, 2.21. So relatively close. And we can now say for the second mode shape, we can do the calculations, or we can see it from here. So for the second mode, if we divide, so it's 14.9, 6.2, 12.4. From robot. And that means we need to divide each of them by 14.9. And this is 1, this is negative 416. 042, and the other one is, sorry, this is positive 0.42. The last one is negative. $12.4 divided by 14.9, 0.832, negative 832, negative 83. And then X3 was in robot 11.7, 14.9, 7.1. Is that correct? 11.7, 14.9, 7.1. And if you look at the signs, they are positive, negative, positive. So this will be 1, 14.9 divided by 11.7 is 127, negative, and then 7.1 divided by 11.7 is 0.61, positive. And that can be checked by hand calculations. So in robot, this is how we could do this analysis. We can also do the analysis by using the dead load. If you had dead and live load, then we can do the new analysis. And let's call it new model, and I'll call it model 2. And now for this one, I'll also put 3 modes, but I will disregard the density. And now I will do the load to mass conversion. Dead load. Dead load. Sorry, no. Dead load, yeah. 1. And add. So this is added the dead load with the coefficient 1. And in X and Z, so it's working in the plane. And if I do calculations and now show the result of model 2, basically it's model 2, the same results. So this would be something we would do if you had live load, dead live load, snow load, or whatever. You could also convert all or part of it into mass.